Here, Komal, I have a pair of safety glasses for you to put on because
thanks.
you and I are going to do a somewhat dangerous experiment. So it's a good idea to be prepared.
All right.
Okay? First of all, do you know what that chemical is? You know what the C stands for?
Carbon.
Carbon. And the H?
Hydrogen.
And the O?
Oxygen.
Yeah, when you put them all together, like this in this form, you got sugar.
Okay.
Yeah. Have you ever burned sugar?
Yeah.
You know, it has a sort of a typical caramel kind of smell. Well, when you burn sugar, you actually free the hydrogen and the oxygen, so you get water, and what's left behind is the carbon.
Yep.
And you've noticed when you burn something on the stove how black it gets?
Yeah.
Well, let's burn some sugar. I'll put in about a teaspoon or so. Get rid of the lump, okay? Now, here's a nice long stick, and at the end of it is a match. So you take the match, and I'll light the match on the end, and you put it down there in the sugar, okay?
Okay.
Okay, put it down in there. Doesn't catch on fire, does it?
No.
Why not?
Because
What do you need to have a fire?
you need oxygen.
Oxygen, and usually it comes from air, right? And
Yeah.
that's what happens when you burn sugar on the stove. Well, you don't need air. You really need a supply of oxygen, and as you said, and here's where we're going to get it. Do you know what the K stands for?
No.
Potassium. The N
Nitrogen.
and O.
Oxygen.
Yes, and it's that bunch of oxygen right there that we're going to release and combine with the carbon in the sugar.
So then it'll catch on fire.
It sure will. Take the teaspoon, put in about a teaspoon or so of that chemical, put it in there with the sugar, and mix it all up. And I'll get rid of these. And notice I have it on a piece of wood here that I use for burning things. Okay, now one of the problems is we have to get it started. So I'm going to put some match heads in the middle. So what you do with the match at the end of the stick is you bring it near those match heads and catch them on fire. So they'll catch the rest of it on fire. And you will soon see that you don't need air for a fire. All you need is a good supply of oxygen. Okay, bring it down there close. And step back over here with your hand. Get ready to stand back. There we go.
That's neat. It's all bubbling.
Yeah, it looks like a volcano.
Yeah, a miniature
And all
one.
we're really doing is burning sugar with a good supply of oxygen.
It's fizzing now.
So what do you need to have a good fire? Do you need air?
No, you need lots of oxygen.
Right. You've written on sheets of paper like this without paying much attention to it, even though you know it comes from something like this. How do you get this out of that? Well, if you look at wood under the microscope, you'll see it's made up of fibers, hollow tubes that run in one direction, held together by a sort of very strong natural glue. To make paper, you have to get rid of the glue and keep the fibers. Of course, first you have to harvest the trees and chop them up into little pieces. The next step is demonstrated with experimental equipment in the lab of the Hammermill Paper Company. Ground wood chips are put into a large pressure cooker. A chemical is added that will help dissolve the glue that holds the fibers together. After heat, pressure, and chemical action, the chips are a soggy mass that looks something like oatmeal, but at least they're no longer held together with that glue. It's now known as paper pulp. After bleaching and adding a color, the pulp is poured into a large tank of water. The water is quickly drained out the bottom, and the pulp is deposited on a very fine screen. The wet paper is sent through a heated press to remove the water, and finally, a finished sheet of paper. Of course, the paper you use is made with giant machines. You see, there are more than 7,000 different kinds of paper, and every person consumes hundreds of pounds of paper each year, so it must be made in huge quantities. 2,000 years ago, the Chinese discovered how to make wet pulp into paper. Today, tons of wet pulp go into one end of a highly automated factory that uses the latest technology to take wood apart to make that bleached, dried, smooth sheet of matted fibers you call paper. It's Scott, I got this snow from the backyard and tried not to pack it down.
Okay.
And you and I are going to melt it in the microwave and see how much water it makes.
Okay.
So first of all, measure the height of the snow.
About 18 centimeters.
Okay. And what do you predict it's going to melt down to?
Probably about 9 centimeters, about half.
About half.
Yeah.
You think half of snow is water?
Yeah.
Okay. Put it in the microwave and let's see what happens.
Okay. How long?
Oh, about a minute.
Okay.
You know what snow is, by the way, Scott?
Just kind of like fluffy ice.
Fluffy ice?
Yep.
Yeah, but that's a pretty good definition of it. Most people think that, that snow is sort of ice crystal, and it's not really. Matter of fact, tiny dust particles in the air attract a little tiny droplet of water, and it freezes, and that's an ice, that's a snow crystal. And the ones that fall down to the ground are maybe 10, 20, 100 of them all clumped together. You've seen pictures of them, haven't you?
Yeah. Is it true that like snowflakes are all different, like unique?
Well, scientists have divided them up into various groups of types of snowflakes, but it is true that no snow crystal is exactly like any other one because of the way the crystal forms as it sticks out, you know, and so forth. And scientists do the same sort of thing that we're just doing, melting the snow, because you see, the snow is sort of water captured up on the mountains, and so when it melts, it's going to run down into the streams and end up in reservoirs for drinking and so forth. So they want to know how much water is in reserve, so they would make a core like we have done here out of this, and then melt it down to see how much water is there.
Okay.
Okay? Is it melted?
Yeah. Well, it's
Almost?
Almost.
Well, close enough probably.
Yeah, okay.
So what does it measure?
Well, 5 centimeters.
Yeah.
4.5 centimeters.
4.5, and was originally what, 18?
Yeah.
So it's less than a third.
Yeah.
And so I say scientists would do the same thing and would do it much more scientifically than we did. But it's amazing how much air there is in a pile of snow like this. I don't assume, Nicola, you've ever made a telescope.
No, I never have.
Well, today you and I are going to make 2 of them.
Okay.
And you need some very exotic equipment, like eyeglasses like this, you know,
Right.
that people buy because they want to magnify it so they can read. And notice this only has one lens because the other half is down here in the front.
Oh, yeah.
See, there's a little hole in there, and I just taped the reading glass on the front. Okay, then the light is going to be brought in here like this and brought back here, and then we want to be able to see the image. So here's a tube that will fit in the other end, and there's sort of like tracing paper on it.
Okay.
Then the other thing you need are tubes like this that you can slide in and out. Tubes like cereal box, you know, round cereal boxes, or tubes that, mailing tubes or something like that, so you can slide one inside the other.
Yeah.
Okay, I'll put this back here like this. Then I want to swing it around because out there in the hall, I put a book there under the lights, yeah?
All right.
So let me sort of line it up so you can see a little bit. And I'll put this out here about like that, and you move that back and forth until tell me what you see.
All right. Oh, wait a minute. Oh, okay. I see it. Oh, I see a little book upside down. It's the same art book.
Right. Now, the reason why it's upside down is this lens focuses the light to a point about like that and then goes out like this.
Oh, I
see. So
see.
it turns it upside down. And you're seeing it on that tracing paper. Now, the other thing you need then is a little piece of a magnifying glass like that.
Okay.
You know, the kind that you look at insects with or read fine print or something like that. And I have it, see, I pasted it right over the end of that little tube like that.
Yeah, okay.
Same like that. Okay, so if we take out the tracing paper and put this in position, now you move that in and out until you can get it kind of sharp and tell me what you see. Go ahead.
All right. Oh, okay. I see a humongous A upside down.
Yeah, now look over the top directly and see what the A looks like, and then look through there.
Oh, this one's a lot bigger.
Yeah, a lot bigger. Okay, now that's one kind. It's called a refractor. The light is bent and, you know, and magnified that way. So that's one type we're going to look at. Here's the other type, which is called a reflector. You know what that word means?
Yes.
When you reflect something? Okay. I've got this one so I can take it apart and show you the important things. Here is a mirror, see it?
Yeah.
Something like a shaving mirror in it that magnifies things.
Oh,
But the light's going to come in through here, hit this mirror, and then be focused back down over here to that little mirror. See the little mirror sitting there? That simply bends the light over here to the eyepiece.
Oh, I see.
Now, first of all, let's put one of those. This is sort of like that tracing paper again.
Okay.
If we put that right here, then I have a top I can put on it. We'll have to turn it around because the light comes in through this end. Now turn it around like that.
Okay.
And you're going to have to look in through this side. Okay, now let me sort of get it in position for you. Okay, now move that in and out until you can see as sharp as you can. See what you see.
Okay. Oh, okay, I see the little book, the art book, upside down, and it's fuzzy, like the first time.
The reason why it's fuzzy is this sort of like wax paper or tracing paper has little grains in it, so it doesn't focus real sharp.
I see, okay.
Here's another lens, just sort of like the other one. Tell me what you see if we put that in position, and you now magnify the image. Try that one.
Oh, okay, I see the same book, the same way as the other time, except it's a lot clearer.
It's not nice and sharp, okay. So those are the two telescopes that two friends of mine have made. One using a mirror like this one, the other using a lens like that.
Oh.
And I have them set outside. So let's go take a look at what real telescopes look like, okay?
Oh, sure.
We'll take a look at this telescope, Nicole. I think you should be able to identify what kind it is.
Well, I think it should be a refractor.
Yeah, and what's happening to the light?
Well, the light goes through down this lens here, and then it reverses and goes through down here to this lens, and I can see it.
Okay, and mine was a homemade telescope, but this one is also but much better telescope because it was made by an expert, even though this is a piece of pipe from sewer.
Oh.
Yeah. Okay, take a look through the eyepiece, and here's how you adjust it. See the little knobs there?
Okay.
Okay, see what you see.
I see a whole bunch of leaves from the trees over there. They're really sharp, you can really see them.
That's because he did a good job in putting it together. Now see that one over there?
Yeah?
So what kind is this?
Probably a reflector.
What makes you say that?
Well, I think that the sun will go down through here.
Or the light, at least, right?
Yeah, the light.
Okay.
And then it would go down here, and there's a mirror down there. And it would bounce off that mirror to a mirror, which is a little one right there. And that would bounce right through there, so I can see.
Now, both these telescopes were made by members of the Royal Astronomical Society of Canada, which is a group of people who get together to talk about telescopes and build them and so forth. And both of them are homemade. But this one is a especially good magnifier. In fact, see that little yellow sign up there?
Oh, yeah, right where the trees
Can you
are.
read it?
No, not at all.
Well, take a look through the telescope.
Sure. Oh, okay, here it is. It says upside down. If you can read this, you are too close.
Very good. Darrell, all you need to do is get a piece of light cardboard, cut it into the shape of a boat, cut a slot in the back, and put a little piece of soap in there.
Oh, okay.
And then put it on the surface of the water. Look what happens.
Oh, it's moving.
Go ahead, put yours on.
Okay.
Try
You
another
start
one.
moving pretty fast. Why does that happen?
Yeah. Well, that's because of a sort of interesting and mysterious, invisible attribute of water that a lot of people don't even think about. And that's what you and I are going to investigate today.
All right.
Now you can do another trick. See, there's a paper clip and a fork. Put the paper clip on the end of the fork and get ready to try to float the paper clip on the water. What's the paper clip made of?
It's made out of metal.
Okay. Notice
So
that
it
I'm winding
shouldn't
this off, I'm scraping the top off like that. I'll explain that to you later.
Okay.
Okay, wait till the water settles down a little bit. Now, slowly bring the fork down and see if you can leave the paper clip behind.
There it goes. It's floating.
Yeah, a steel paper clip floating.
Why does it do that?
Well,
It's
that's
just...
based on that same sort of invisible attribute of water. Here is a piece of ordinary baker's string.
I see.
See how it's in an oval?
Yeah, it's sort of an irregular
Yeah.
shape.
There's a piece of soap. Touch the soap to the center.
Okay. Oh, turns into sort of a circle.
Yeah, keep touching it again.
It moves away from the soap.
Yeah, and now you made a nice circle.
Uh-huh.
Well, let's see if we can't find out something about this mysterious thing that's on the surface of the water. Get the paper clip out of there. And now I'll do this again. First of all, if you're going to do these kind of tricks, you should get clear, cold water, nice and clean, no soap in it. I put it in a tray, and I put wax all around the edge so that you can sort of heap the water over the top.
Oh, so the wax is keeping the water in.
Right, sort of keeping the water in so that you can load it to the very top with water. Then, here's my old favorite stuff called lycopodium, which I will sprinkle on the top, and so it'll make the top surface visible. You could do this at home with pepper. Water's still moving around a little bit, see?
So the lycopodium just, it shows the water more.
Right, it's just making the surface visible.
Okay.
Now, that bar soap, touch it right in the center.
Right. Oh, it does the same thing as the string did.
Right. Now, see if I can explain why and see if you understand it. As you know, water is made up of molecules. Below the surface, the water molecules are all around each other. But up at the top surface, there's air up above it. So the top surface water molecules are sort of pulled together because there's nothing pulling them up.
Oh, I see.
So that means there's sort of an invisible skin. The molecules are closer together on the top surface of water.
So they're pulled together on the top.
Right. And when you touch a bar of soap to it, the soap molecules dissolve in the water and get in between those water molecules, and they don't pull as well, and so they go apart.
So it breaks the surface
Breaks the surface tension, it's called. And now you see why I did this?
Because that way you can start with a new surface.
Get rid of all the contamination on the surface, and you can start over. Now, can you explain the boats? Where one of the little boats is down here. Can you explain what made the boats go forward?
Well, since soap separates the surface tension, they're going away from the break. They're
Right.
going
In other
towards...
words, it's the surface tension behind the boat that's being broken, so it is pulled forward or around in a circle in that case because the soap is off center a little bit. So that's what makes them go zooming around. Now get your fork and the paper clip.
Okay.
If you do this at home, you don't have to use one of these. You can just fill it up with new, fresh, clean water. Okay,
All right.
See if it's nice and clean. And when you do tricks with surface tension, you have to make sure your hands don't have any soap, because any kind of soap that gets in there, be careful. There you go.
There it goes.
Now, why is it floating?
Well, it's floating because the surface tension is broken, but it's holding it up.
No, it's not broken in this case. All you're doing is sort of putting the paper clip on the top of the surface and it's sort of bending down like rubber. Like
Oh, okay, so it's supporting it.
Right. And in fact, there are several things that you do that try to get rid of that surface tension. In fact, notice soap broke it? So when you use soap to wash dishes or your hands, it's breaking the surface tension and making the water wetter.
Oh, I see.
So you can break it up so you can clean up stuff better. So when you do this at home, be sure to get nice, cool, clear water with no soap in it. Now for the real test to see if you understand it.
Okay.
You've had strawberries and raspberries and things like that.
I love strawberries.
And they come in a basket like this too, right? Full of holes.
Yep. There's holes all over
You couldn't
it.
possibly float something like that, do you think?
I don't think so.
Well, here's a pan of water. Try it.
All right. There it goes. It's floating.
Why?
Well, the surface tension is holding it up.
Yes, and if you look closely, sometime when you try it, you'll see the water sort of bent down in each one of the places where the bars go across.
I
So
see.
you're floating it on the surface tension. How could you sink it?
Using soap.
How about spraying a little soap in the bottom?
All
Watch
right.
what happens. Down it goes. Keep going.
There it goes.
Stroll through a park, and you could see a statue like this. Since this is the way most statues look, you may think this is the way it's supposed to look. Actually, it should have a gleaming finish like this. That's how a bronze statue looks when it's first put into place. Sulfur in air pollution has chemically reacted with the copper, tin, and other metals in the bronze alloy. The chemical reaction is speeded up by rain, and in some bronze statues, it's gone so far as to make them into active batteries. A solution is a visit to a sort of hospital for statues at Washington University in St. Louis. This patient is obviously in bad shape. The treatment calls for the removal of the layers of corrosion by a process developed by the Sculpture Conservation Laboratory. It works something like sandblasting, but instead of sand, tiny glass beads are used. The beads are shot through a nozzle to blast away the layer of corrosion without harming the metal underneath. Sometimes, however, a statue is too large to be transported to the St. Louis lab, so the team goes to the statue. They've already removed the major corrosion with the glass beads. Now they're concerned with the details. To restore the star's rich brown color, it's heated with a gas torch. Once the color of the entire statue has been restored, every inch must be brushed to remove any residual materials from the earlier processing. Then a liquid plastic is sprayed onto the metal to form a barrier. The color of the statue shows through, but the air pollution is prevented from immediately starting to turn the brown surface green again. Eventually, more and more statues will look like they're supposed to, thanks to the art conservators from the Hospital for Statues. Jackie, here's a meter stick and a C-clamp. And I'm going to clamp the C-clamp way up here near the top. In other words, adding a weight to the meter stick.
Yeah.
Now, put your hand out. What I'd like you to do is to take it like that, hold it with it, and now balance it.
Balance it?
Yeah, balance it.
Okay.
You got it?
I'll try.
Okay.
Okay, here it goes. Oh,
Okay, very good. Grab it now.
Okay.
Now, let's move the C-clamp to the center of the meter stick.
Okay.
Will it be easier to balance or harder?
Easier.
Okay, you'll see. It's all yours.
Okay. Try it again. Oh.
Harder?
It's harder.
Yeah, why should it be harder to balance it when the weight's in the middle than when the weight's way up here?
I don't know.
Well, let's think for a minute about what you're doing when you balance something. Okay, put it down there and hold on to it. When you see this start to move, what do?
I move it that way.
Yeah, you move your hand under it. Right? If it moves that way, you move your hand over here.
Way.
Okay, now this is a great big arc pivoting here from your hand all the way up to the end of the meter stick. So when the weight's way up here, this whole mass would move through an arc like that.
Yeah.
So you have a fixed amount of time. Now when you move it down here, because there's so much mass here,
there's only this
the arc
much.
is shorter.
Yeah, and it's...
So you have less time.
Yeah, to move it.
Right. So go ahead, practice with this, because once you get the principle down, I have a dangerous trick for you to do. Go ahead, practice.
Okay.
Okay, very good. Now that you know the principle involved.
Yep. Oh, okay, I'll try that. I sure am.
See if you can get it all the way to 7. I'll count.
Okay.
Got it? All yours. 1, 2, 3, 4, 5, 6.
Almost.
But you get the general idea?
Yeah.
This one is a little easier a little harder because it wiggles.
Yeah.
But it makes it much more dramatic. Well, congratulations. You're a good balancer.
Thanks.
It bounced right through there so I can see.
Now, both these telescopes were made by members of the Royal